Hello, welcome back for the second in the series of talks on generalizing from varieties to schemes. This is the second in the series of bi-weekly talks, so continuously interrupted, not continuously ongoing. And where last time we described varieties in their classical setting, and we just left off talking about what sheaves are. I'll pick up today again, re-explaining sheaves, just to bring all of the people who are here present in the audience up to speed, and also because last time the sheaves that I defined were sheaves of sets. Really what we're going to be using are sheaves of rings. It's a minor modification, but it's worth discussing the slight difference. And after I have done that, we will finally define the morphisms between varieties. Because we didn't do that last time, all we did was define the varieties themselves. So if you're a good mathematician out there, you might be asking yourself the question, how do I know when two varieties are the same, isomorphic? I need to know what the morphisms between them are first before I can ask such questions. And we will see that sheaves, or in sheaves, lies the answer. So, sheaves of rings. So just as in last time, we had a topological space, and for every such topological space, we could associate the category of open sets on that topological space. So objects are opens subset X, and morphisms were just inclusions of open sets. So if I have one open subset U contained in another open subset V, then we say that this is the unique element of the set of morphisms in my category from U to V. So it has one element, and compositions just follow from the transitivity of the subset inclusion. For each one of these things, we had this F, which was just a procedure for sending these open sets into previously the category of sets. So for every single one of these open sets U from our space X, we had some set somewhere. Now, what I'd like is for us to be in the category of rings. And when I say rings, I mean commutative rings with unity. I'm not going to keep saying commutative rings with unity because whenever I say ring, I just mean one of those. We're never going to be talking about a non-commutative one. We're never going to be talking about one without unity. Okay. So every single one of the associated objects to the open sets in our topological space is going to be a ring, and every single one of the restriction morphisms from the set of sections on a larger open set to the set of sections, or rather from the ring of sections on a larger open set to the ring of sections on a smaller open set. Well, because these guys are now rings of sections instead of sets of sections, this restriction morphism is now a proper ring homomorphism. It does all the things that a ring homomorphism is supposed to do, not just a set function anymore, like I previously defined it. So we want, so there were other properties that I mentioned besides just the existence of these restriction morphisms. Whenever I have a double inclusion in my category, so that's an open set contained in a second open set contained in a third open set, it is the same to restrict down all the way from W to U as it was to first restrict from U to V and then restrict from V to W. So just like if you were restricting a function and you restricted it to one subset and then a subset of that subset, it's the same as restricting all the way down to the small subset all at once. It doesn't matter whether you do it in stages or not. In addition to this...
Backwards? Yeah, backwards? Yeah.
Nope, it's not backwards.
You have to go from U to V and then V to W.
U to V, this is U to W. This is going from U to V, and this is going from V to W.
So the first one, though, is actually going from V to U, right?
This one right here is going from...
No, not the first one. The first is when you wrote U, V. So right next
Oh, yeah, you know what? Yeah, 1 second. So, yeah, this guy right here, he's going from V. Yeah, you're right. So, excuse me. This one. Thank you. You caught me. I did this last time, too. For whatever reason, reversing these indices always just turns my brain off. So, yeah, no, you guys are absolutely right. Because what we should be starting with sections. I don't have it written down anywhere. But we should be starting with sections on the open set W. So this map, no matter what it is, it should have W involved in it. It should be eating W, guys. And if we go back here and look at how I wrote this down, in order for this thing to be eating stuff from W, it has to have that guy there. So we know we're supposed to put W right here and V right here. And that tells us same business right there. So yeah, other way around, it's always the opposite of the first way that I write it. Basically, if ever you're watching me give a talk about this, you can assume it's modulo the other direction that I did it. So there we go. So this is enough to make a pre-sheaf of rings. In order to make it a sheaf, we also need it to be the case that for all open sets, or I suppose I can be more specific since I went ahead and gave it a name. I named the daemon, so I might as well use it. So for all open sets in our category of open sets, and all open covers, of U with collections. So just like last time, we have compatible families of sections on each of the cover elements. So Fj in the, whoops, not F, big Fj, but Fuj. So a bunch of elements of our rings of sections such that whenever we use the restriction morphisms to get down to intersections, what we wind up with is that these things, there we go, take a drink every time you see me erase with my hands instead of the eraser that I'm holding in my hands. You're going to pass out by the end of this talk. But anyway, so yes, what this is saying is that all of these section elements that I've got in my family here, they're compatible on the intersections of my cover. Once I know that I have such a compatible family, then in order to be a sheaf for any such compatible family, there must exist a unique element of the global section, the global ring of sections, here F of big U in this case. Sorry if that's getting a little hard to read. Such that now his restriction to all of the cover elements are exactly, so we restrict down to the smaller one, yep. Ui, U is of F is equal to Fi. So all of his restrictions are exactly all of the family elements that we gave. That's not my best writing that I've ever done in my life.
Sorry, are Uj covering U?
Yes, I didn't write anywhere. All open cover. Open cover. There's the second time of U. There we go. So yeah, so whenever we have a topological space and an association of commutative rings with unity to all of its open sets that is compatible with the idea of taking intersections in the same way that functions are. And so that whenever I have one of these compatible families of sections for some given open cover of an open set, I can go ahead and glue uniquely all of those sections together into one global section on my big open set ring. So there we go. That's what it means to be a sheaf of rings. Very minor modification from last time because the only thing I really did here was replaced set with rings, and I mentioned before that each one of these restriction morphisms is not just a set function anymore, it really is a ring homomorphism now.
So this is just going from the pre-sheaf to a sheaf, you're literally just saying how much does locality determine global?
Exactly, yeah. Can you go ahead and take a bunch of local things that all agree with each other and honestly turn that into a global thing? And on a sheaf, the answer is yes. On a pre-sheaf, the answer is maybe. Right? You don't know necessarily. So there we go. So this, and whenever we have a topological space together with a sheaf of rings on it, we call that a ringed space. So it's a space together with a sheaf of rings. Morphisms of ring spaces. So these are honest objects that you could go ahead and study from, try to study their geometry or their topology. A topological space equipped with a sheaf of rings. And if you were to do that, you would want to answer the basic question of when are two the same? When do I know two are isomorphic to each other? So I need to have some sort of mapping, some sort of arrow that communicates with the two pieces of structure that a ring space has, namely the topological space and the sheaf. So morphisms for topological spaces are just continuous maps. So it seems pretty obvious then that we should look for continuous maps that do some extra stuff relating to our sheaves. And that is in fact exactly what we do. So for ring spaces, xf and yg here. And the way to think about it is it's going to work in exactly the way that a pullback of functions works. If I had two topological manifolds and I was thinking about all of the continuous real-valued functions on them, then for any continuous map between topological manifolds, I could go ahead and pull the functions on my codomain manifold back onto the functions on my domain manifold just by composing them with my continuous function. So that would give me, if you think of the continuous functions on my codomain as the sections of the corresponding to the open set that is the entire space, then this is a ring homomorphism from that set of sections, from that ring of sections, to the ring of sections on my domain manifold, for the sheaf in question here being the sheaf of continuous real-valued functions. So that's the sort of idea. We're going to end up taking sheaf elements from the codomain somehow and mapping them to sheaf elements of the domain. Ring spaces, a continuous map. Is a morphism if for every open set there's third time. I can't even stop myself from doing it like as it's happening now. So for all open sets, there exists a ring morphism f sub u that goes from the sections of y's sheaf at u to the sections of f's sheaf at f inverse of u. So like we pulled back the continuous functions from that open set onto the pre-image open set on our domain. But this thing needs to be compatible with the structure that sheaves have. And the structure that sheaves have, or rather the structure that pre-sheaves have, because technically this wouldn't be any different if I...
So all I do is just compose sections of U with F?
When what those sections are just continuous functions, or rather just functions into some other space. the rings from our sheaves of rings don't have to be rings of continuous functions or rings of functions. So composition might not necessarily make sense. Exactly. But it will always go that direction, whether it's composition or not. Okay, but we also have these restrictions for our pre-sheaf. That's the other bit of structure that pre-sheaves have and sheaves have. So a morphism of such things should see and respect such structure, and in fact, it does. So the way we think of it is if I went ahead and restricted if I just go ahead and put a G up here, then we can pretend that this is the restriction that corresponds to our sheaf G. And this will do exactly what I want if I was restricting on one side from V to U. So I'll go ahead and put FU, circ, and then rho, capital G, UV. So what this is right now is a map from G of V. Whoop, so let me write this over here. G of V. It passes through our restriction morphism that sends it to G of U, and then it passes through FU, which sends it to F inverse U. Tried to make it arc up a little bit. So in order to get this same sort of thing to happen, but to result from restrictions on the other side, I need to have, so F, and I'll go ahead and wait to put in subscripts for a second, because instead I would want this to be V, because that would have these things domains matching up. But then I would want to have the restriction here be the restrictions corresponding to F. And instead of having U and V, I want to have the preimage of U and the preimage of V. So this is a commuting square, because it's two compositions equal to each other.
So this is coming from the sheaf condition?
Exactly. This is coming from wanting this collection of indexed ring morphisms to respect the restriction morphisms of our sheaf. The restriction morphisms are the structures that pre-sheaf and sheaves has. And so if this is meant to be a morphism of topological spaces and the sheaves on them, then it better respect that structure. And the obvious way to do it is to have a square commute. And this is the obvious square to commute. All right. So there we go. That's what it means to be a morphism of a ring space. You are just a continuous map that preserves the sheaves. How do you preserve sheaves? You send sections of the codomain sheaf to sections of the domain sheaf in a way that's compatible with restrictions. That's all it takes. So why would I bring this up, right? Because these ring spaces aren't the varieties that we were talking about last time.
So, I'm sorry, so is it possible to write down explicit action of this map FU on G of V?
Any collection of ring morphisms that will satisfy this guy and can be associated to a continuous map flies. So the ring morphisms don't necessarily have to come from information just belonging to the continuous function.
Right, so like if I specify the sheaves G and that, would I be able to write down this F of U explicitly?
You might be able to come up with...
If it wasn't like continuous functions, but like you're saying.
Those are the ones for which it is easiest to come up with, like continuous or smooth functions, because then you write this down as literally just the action of this thing. Yeah. Exactly, pulling back by composition. But in general, it doesn't have to be that. It could be something else, some other set of ring homomorphisms that arises some other way and just manages to satisfy this. That will also count.
So in practice, if you want to find this amount of FU, you just try to find the function which satisfies this.
Exactly. You just an indexed collection of ring homomorphisms, indexed by the open sets of the codomain, that satisfies this property.
Okay.
Because, and you'll notice here, the only way that F enters in is there.
Yeah.
So there is a relationship between the original continuous function F and this indexing, but technically, like as long as you satisfy this, there could be multiple different indexings of ring homomorphisms corresponding to the same continuous function, where that clearly wouldn't be the case if I was talking about the homomorphism induced by pullback, right? Only one way you could do that.
Maybe my question is, what's the existence proof for F? Is it something easy, or is it like?
It varies by, it can vary widely depending on what the ring is.
Particular choices.
Incredibly sensitively, yeah.
Okay.
All right, no problem. All right, back over here then. So yeah, so why talk about ring spaces and morphisms of ring spaces? Well, last time we talked about affine varieties, but we hadn't yet discussed how we map between them, the morphisms of affine varieties. How do we know when two are isomorphic? And in fact, it's because we were going to have to write down a sheaf of rings on the affine variety in order to do so. And so I thought it might be prudent to actually write down the definition first so that when we go ahead and write this thing down, we recognize it when we see it. We know what we're looking at. So let's return for a moment back to affine varieties. So recall we have two functions v and I. V sends sets of polynomials to the set of all points in affine n space on which all of the polynomials vanish. And I takes a set of points in affine n space and associates to it the ideal of all polynomials that vanish on that set. So we have these two things. And we also have the idea that we can think of varieties as particular subsets of affine n space. They are irreducible closed subsets. So that's one way that we can think about them. But they are also algebraic. So, yep.
I think I saw that. You said V is just an algebraic term, or is it an affine?
V, no, oh, I'm sorry, I used V in two different places here. You know what, I should keep using X for this, so I'll never have to worry about that. V is a function that I've already named. Thank you for calling me on that. V is a map that associates sets of polynomials to points, sets of points in affine space, the points where they all vanish. So yeah, so one way is as an irreducible closed set. Another way is as the vanishing set of a prime ideal. So P prime ideal. In the algebra of polynomials that we care about, which is this for n space. Okay? And last time we described the Zariski topology on the entirety of affine space. Because a variety, any affine variety, is going to be a subset of that affine space, we can go ahead and give it the subspace topology coming from the ambient space it lives in. All of its open sets are just intersections of open sets in affine space, Zariski open sets, with our affine variety X. And using that, we can go ahead and define what it means to be a regular function on an open subset. So I'll use W, be an open subset. So we say that a map on our subset W to our field is regular on some open subset of its domain if there are polynomials, a pair of polynomials, if there exists polynomials g and h in A such that so H, who's going to be our denominator here, he can't vanish anywhere in U. So there are no x in U such that h of x is equal to 0. And f restricted to U is equal to g restricted to U divided by h restricted to U. So on this open set, on the rest of W, who cares what it's doing right now? But in order to say that it's regular on that open set, then it just has to coincide, its restriction just has to coincide with a fraction of polynomials, where the bottom polynomial never vanishes. So if f is regular on uj, and I should maybe go ahead. Here's the first time that I've used the eraser properly. So now f global function on the entire affine variety. So if this guy is regular on uj for each I'll go this. For each little j in an index set where the set of all these guys is an open cover.
So here it says there has to exist an x in U such that h of x is 0.
Oh, wait. There does not exist.
Okay.
I forgot to slash through. Thank you for calling me on that. Yeah. There can't be any of these. It never vanishes in the denominator. This is an actual well-defined, totally reasonable map everywhere where you just get it by evaluating points.
And just to make sure, W is an open subset of an affine variety.
Yep, open subset of this affine variety from the subspace topology coming from the Zariski topology on affine space. All right, and so yes, if we've got a global function which for every element of an open cover I can hear him out there. But anyway, if I have a globally defined function which is which is regular on every single cover element for an open cover, then we say that f is regular. So being regular, which is the condition that we use to define being one of the members of our global polynomial coordinate ring, that's actually a local property. But it's not defined just by taking polynomials. Locally, it's actually defined by taking quotients of polynomials, by rational functions. It turns out, though, that when you go ahead and take the set of all regular functions, the collection of all regular functions on the entire space, on the entire affine variety, that coincides exactly with the original definition of the coordinate ring that I gave you, the one that you got just by doing this, which was before what I was mentioning. I had to go through all this to explain that, which is why I said that this was just the easier way to present the coordinate ring. Yeah, that's faster, but now we can see that this is like honest-to-God polynomials.
Are you saying that all regular functions are just rational functions?
No. It depends on where you mean. On these open subsets, on these proper open subsets, yeah, they can be given by these.
But globally, what do they look like?
They look like polynomials. This is the original coordinate ring of polynomials. So the fact that the denominator doesn't vanish anywhere for every single one of its local representation actually gives you the effect that you can glue it together into one big polynomial on the whole thing. Okay, and so so for every single open subset of our affine variety, we have this ring now of regular functions. The regular functions form a ring. You can multiply them together, you can add them, you can scale them by any constant. The constants are among them. So we do have, in fact, a commutative ring for every single open set of our affine variety. And because these guys are all functions, the restriction morphism is just literally restriction, like going and taking a restriction of functions. You don't even need to go and check the sheaf condition because the sheaf condition comes from function restriction. So function restriction automatically does it. So here we are. We have a sheaf of rings on our affine varieties. And it's actually this sheaf of rings that we use to define when you are a morphism of varieties. And again, even though it might look like this is suspicious, because before we talked about a coordinate ring of polynomials, this is just a local condition, and being a member of that coordinate ring of polynomials, that actually was a local condition. Just when you are a member of the global sections, you happen to be just a polynomial, not a fraction.
So if x was equal to an of f, and f is c, regular functions just be polynomials?
Yes, the regular functions on affine space are just the polynomial functions. Well, when you're talking about, again, global, the entire space. As soon as you talk about an open subset, now it's just the fractions where the polynomial on the bottom never vanishes on the open subset in question.
Well, what I wanted to make was like you have this ratio of polynomials with bottom ones, never zero on C, but that can't happen with polynomials, right?
The only way it can is if it's constant.
It's constant, yeah.
So yeah, that's why proper open subset, good and important.
Okay.
It's why being global forces you into being a polynomial, essentially, is what you're getting at. Okay, so, but here we go. We've got a sheaf of rings for every single one of our affine spaces, and now I can go ahead and tell you that morphisms of varieties I can go ahead and tell you how to map from one variety to another. So let x and y be varieties of our affine space. So we already know that they've got the subspace topology coming from the Zariski topology. So I can talk about continuity of functions between them. That's important. If we recall from the definition of morphism of ring spaces, I needed to be able to talk about what maps were continuous first before I ever even posed whether you preserved sheaf structure or not. That was because at some point I needed to pull back an open set by that function, and if I couldn't do that, then no dice. All right. So the affine varieties, a continuous function, f going from our first variety to our second variety.
So just to make sure, you intersect the Zariski open sets with what again to get the subset?
With the individual varieties. So I want the open subsets of x. Zariski open subsets of affine space are intersected with x. If I want the open subsets of y, I take the Zariski open subsets of affine space and intersect them with y. Yeah. Subspace topology is always just the intersection of the opens of the ambient space with the smaller space. And just like before, what's going to happen is I can use such that for all open subsets open, this thing is a function, and these things are actual honest-to-God functions. So I can, before we were talking about how we come up with the ring morphisms, in this case, I can make the choice of just pull back. And the question, and this guy is going to be exactly. This guy is going to be a ring morphism when that actually works out. If for all openness and all regular maps, so I need a regular map. So he's going to go from I will name this sheaf here S. This is my sheaf of regular functions. So I want to go from the continuous function that goes from the, that's not what, he belongs in this. I was losing my mind there for a second. Belongs in the sheaf element corresponding to U for our open set, and I suppose I should mention like X here. So this Y. There we go. Now everything's right in my brain. Okay, for all of these guys, I want that the composition with F, specifically with his co-restricted and restricted version, I want this guy to be regular. So, sorry, I lost myself in the middle of that, and it was a long writing process, so I'll just go over it again really quickly. So again, a continuous function is going to go ahead and be also a morphism of varieties if for every single one of the open subsets of the codomain and every single one of the regular functions on that open subset, I can go ahead and pull it back to a regular function on the pullback of the open set by f just by composing with f. So whenever f does this, we go ahead and say that it is a morphism of varieties. And now we can very clearly see that varieties are just a subcategory of the category of ring spaces. What it takes to be one of their morphisms is, well, in addition to satisfying the criteria that it's compatible with restrictions, it is exactly, as we were talking about before, the special case where the way we generate all of these ring homomorphisms is specifically through composition. So it satisfies this extra concreteness property as well. But, you know, so modulo concreteness, we are a full subcategory of the category of ring spaces whenever we're working with affine varieties. And so, you know, that's a nice category to start looking whenever we think about generalizing varieties. The structure that we're using, the way that we're analyzing affine varieties, the magnifying glass that we're using, is the same magnifying glass that we would be using if we were just in the category of ring spaces. Okay, so we know how to say when an affine variety, I'm going to start over here. I'm going to use the whole board again, but we know when to say that an affine variety is isomorphic to another affine variety. So now we're actually in the position to discuss something that I mentioned last time, which is that you can reconstruct a space from its coordinate algebra, from the coordinate ring of polynomials on it. This is important because the procedure that we use to do this is going to kind of be informative for how we're going to go and build actual affine schemes. It's going to proceed along very similar lines, but there's going to be some slight differences that come along as well. So let me go ahead and finish this up. And for the one of you in the audience who's in functional analysis with me, you will recognize a bit of this because the procedure that we use to construct the underlying variety from a coordinate algebra has a lot in common with the one that we use to construct the underlying space from a Banach algebra when we're doing the Gelfand transform. So, if you know, you know. Alrighty, first things first though, we're going to start with the simplest example, the simplest variety. How do we recover affine n space from just the polynomial ring in n determinants over our field F? Well, so for all maximal ideals this is equal, I'll call this A so I don't have to keep writing that down over and over again. So for all maximal ideals, we know that so the quotient of A by J has to be a field. This quotient, though, is taking place in the category of K algebras, though, so there's only one field it could be. okay, F algebras. So there's only one field it could be, F. And in particular, there is a unique isomorphism from A mod J to F, because all morphisms of F algebras have to preserve exactly the elements of F. So the only things that are in these guys. So there's only one way of doing it.
Tell us what J is.
Well, I haven't. All I know about J is that it's maximal.
Yeah, but classifies all maximals.
It tells you that the ideal associated to a vanishing set is radical.
Okay. So then am I thinking of preexisting? No, they're preexisting?
Not as far as I can tell. All right. So, okay. So here we go. We know this, and this allows us to construct the map in this following map. So I can make a quotient that goes from A to J, and then I can go ahead, rather from A to A mod J, and then I can go ahead and use the unique isomorphism that I mentioned existed in order to compose these two to get a homomorphism from our original algebra directly into F, made in the obvious way. I don't have any other way of making functions than composing them, right? I'm just like the rest of you. I put on my pants one leg at a time. Okay? So for every maximal ideal, we have one of these homomorphisms into our field. And we know that we have the elements, we have the elements xj in our algebra, right? The indeterminates that we had joined in there, they better be in there. So we have these guys in here, so we can go ahead and pass these guys through this map to get a collection, xj, x1, there's the fourth time. That's 4 shots for you people at home. I'm getting tipsy now. All right, so this, just by passing our indeterminates through the ring homomorphism that we got from our starting maximal ideal, we wind up with an n-tuple of points in F. So there we have recovered the set of underlying points from affine n space. I don't have affine n space written anywhere here right now, but over there. They have the same underlying set of points I've just shown, or rather, I haven't shown, but this is the procedure that we would use to show that the maximal ideals are in one-to-one correspondence with these n tuples of points in F. And I'm not going to go through all of the details of showing that that is actually a bijective correspondence, but it is a bijective correspondence. And more importantly than that, the affine structure, that is what makes affine space, is preserved across this transformation. So what it means to be an affine map is pretty easy to understand on n coordinates. You can take linear maps on them and then also translate them, right? That's what it means to be an affine transformation. So an affine transformation on this side has the equivalent affine transformation on the side of maximal ideals. And if you're wondering, well, how the hell do I do an affine map on maximal ideals? Well, that is going to be something in here. You apply that same affine transformation that you applied to this guy to the indeterminates. And that produces the mapping on all of the elements in this guy, including the mappings on ideals. So you will find that the affine structure on either side of this transformation, going from maximal ideals to points in Fn, is the exact same, meaning that you could think of either all these points in Fn with the Zariski topology and its usual affine structure, how you're used to, or you could have started out with your polynomials in n determinants and just considered your space underlying it to have been the space of all maximal ideals. And generating the one extra bit of discussion, I suppose. How do I generate the topology from the algebra? because I've talked to you about how to generate what the affine structure would look like out on its side, or at least I waved my hands about it and mentioned that it would be preserved. How would I have produced the topology on that set of points just from the algebra alone? Well, what I would have done what I would have done is I would have taken any old ideal of my algebra, and I would have asked the question about what is the set of all maximal ideals that contains my given ideal. I would have called the set of all such maximal ideals a closed set. You might think, but wait a minute, I thought closed sets were all algebraic sets. They all corresponded to radical ideals. Well, yeah, but I told you it also doesn't matter whether or not you take the vanishing set of an ideal or of the radical ideal. It's going to give you the same thing. That's essentially what ends up happening here. So the Zariski topology on the maximal ideal space can be stated as just those closed sets are whatever sets, for any given ideal of our original polynomial algebra, all of the maximal ideals that contain it. That will be the closed set that corresponds to it. And then again, open sets will always just be complements of closed sets. So we can establish the Zariski topology on affine space and the rest of its affine structure. All of affine space that we know of and care about can be very easily recovered as the space of maximal ideals. All right, nice. Now to varieties. So varieties. So there's a similar discussion to be had. So let A prime. Now, instead of starting off with just the simplest possible case of n indeterminates in our field, ooh, how much time? No way. How did that even happen?
Is it good or bad?
That's 10 minutes left. There's no way I'm going to be able to get to it. But I guess I'll get started on it. I must have been going really, really slow. My apologies to the audience. Anyway, so in order to construct varieties, I'm not going to be able to, I'm going to need something slightly more general than this, but I'm also still going to need some constraints on it. So in particular, I'm going to need this algebra to be an F algebra. So an F algebra, finitely generated, with no zero divisors. Zero divisors. Again, I'm not going to be proving anything because I clearly don't have the time. But with these conditions, we'll be able to proceed through the steps that I end up giving you. So those steps are, for such an F algebra, I will be able to come up with an n, and I will be able to come up with a prime ideal. So there exists n and a prime ideal I'll use P for consistency. Subset A, where this A is the same A as this A, right? Because I've got the n, so that with enough indeterminates, I can find a prime ideal in this such that this is isomorphic. It's isomorphic to A mod P. So that's first things first. For any of these algebras that are sufficiently nice, I know that I can actually realize them as a quotient algebra of the ring of polynomials in some number of determinants. That's the first step. So the next step, and this obviously, why do I care about this? This gives me access to the quotient map. Oop. So P, I've got access to this quotient map. Oop. And because I know that these things are isomorphic, I also have an isomorphism. So, oop. He's going to go, in order to make my life easier, because it's hard enough already.
What's n? Does it exist n and a prime ideal?
The number of
Yeah, you're right. Thank you.
Number of infinity, you just said it.
Yes. No, but I should also tell you, like, what it is. So, but that justifies my use of pulling out, because, like, why that one? Why that n, right? But anyway, with this, That gives me a map from, by composing, I can get a map from A to A prime. And now, when I get a maximal ideal on, so J prime maximal ideal corresponds to a homomorphism into F, just like it did on the entire affine space. Ideal gives the following, I'll call it also that. Why not? I'm not using that over here anymore. Yeah, no, you know what? I'll give it a new name. I'm frightened. There we go. J. And what I want to do is when I quotient by this guy, actually, I'll skip that part. We just recognize that there will be a unique isomorphism involved. I can always wind up with, for any maximal ideal, one of these guys, a morphism into F. And now, when I go ahead and compose it with these guys, long string of morphisms will go ahead and get me a morphism from A all the way into F, which corresponds to a maximal ideal in the affine space. I erased affine space. But it corresponds to a maximal ideal in affine space, as we saw already from this argument. So from this, I got from this, where we got it? From this maximal ideal. That's a problem. OK. Maximal ideal such that, no, I did that right. Where was the ideal that I wanted? OK, no, this is the ideal that I wanted. OK, yeah. Sorry, losing my mind here. This is the last thing we'll talk about because I'm unraveling. But to any maximal ideal of the algebra that we started with, the one that we're trying to construct a space out of, I can go ahead and associate a point in affine n space. The way I do that is I compose these three maps together to get a homomorphism from my algebra, or from my coordinate ring on all of affine n space into F. That will correspond to a maximal ideal. The kernel of that map will be a maximal ideal of affine space. In other words, a point of affine n space. So that is, I can associate the maximal ideals in my coordinate algebra to points in affine n space. So I won't be able to finish it this time, but next time I'll finish showing how the set of all of these maximal ideals corresponding to all such relevant points in affine n space, we can give a topology in the same way that we gave the affine space a topology, and then we can give it a sheaf of rings in order to test whether or not it's isomorphic to the underlying affine variety in n space that we construct. So we will go through some procedures here, but the ultimate aim is showing that this procedure of starting with algebra and building a space leads us to the same algebra on top of it afterwards, so it's faithful on the algebra side. But in the midst of verifying that, we also sort of see this procedure of building a space out of an algebra. This is going to be instructive for when we want to go ahead and view any coordinate ring as the coordinate ring of some space, because then I can just take that coordinate ring and build the space on it that I care about. So that's where I'm going. Sorry if it was a little hard to follow this time. Any questions before we go ahead and... Oh, yeah, no. So once again, this is bi-weekly, so I won't be here for... It's bi-weekly? It's tri-weekly. Tri-weekly. I'm sorry I said that wrong at the very beginning. I won't be here for another 2 weeks. There will be other speakers, but on the third week from now, I will come back to finish up this talk, and we will go ahead and finish talking about how we can see... finish constructing the sheaf on the maximal ideal space that we get from such an F algebra, and then see how we can generalize that to eventually get to affine schemes. There's with 3 talks, with 1 more talk left, I don't know I'll be able to do it, but with 4, I think I might be able to pull it off. Thank you.
Is weak Nostalgic sets. That's the name of that. And then regular Nostalgic sets is what you present.
Okay. Yeah, that makes sense. Any, oh, okay.